So yesterday you had a taster to OpenMP. Yeah, there were some lab sessions and so on, and there were a few examples. Really the best place to get examples of OpenMP is to get hold of the specification. So if you go to OpenMP website, the OpenMP forum website, and grab the specification, the majority of it is examples. So the specification is much shorter than the number of examples in there. Hundreds and hundreds of all sorts of things, some of things which I go along and still learn things, particularly about things like tasking constructs and new things in OpenMP3. So I'd certainly recommend that you go along and have a look in there. But so to run an MPI job, you've seen all this. I'm going to skip over most of these things because we were 15 minutes late and you probably had a look at this yesterday anyway. Parallel regions, OMP parallel, Pragma, OMP parallel, depending on the language you're looking at. Just run it. Set the OpenMP num threads environment variable, run your application. If anything more simple than a hello world example, you need to give consideration to private or shared. Okay? This I will reiterate because it is very important. We've had people who are experts who are running on our systems who we typically have 3 main users who run hybrid codes at the moment that they've written themselves. And they have different strategies as to whether they go in and say default none, there is no default for private or shared, I will declare every variable in this parallel region explicitly to be private or shared. Others will go in and say assume they're all shared unless I tell you that they're private, and others who say assume they're all private unless I tell you they're shared. You decide what you think is easiest, but if you go in with the default none and explicitly state it, you're less likely to have a problem. Okay, you declare this when the parallel region is declared, which may be if you've got an application where you can do things at a really high level just once. And then you know what private and shared data is because you would have looked at that yesterday briefly. But there are some other options to do with first private and last private as to whether or not there's some variable given a value on entry in there, or whether the last iteration of a do loop leaves a value in a variable. And thread private copies and reduction variables. I think there was an example there of reduction as well. But it's very important to get that right. So that's the most simple way you can get of parallelizing an application. That was to do fine-grained loop-level parallelization. This is the incremental approach that most people will take to begin with for when they're particularly doing examples. You just go in and at every loop you make it a parallel region, you put a parallel do directive in there. Or in C++ parallel for. You can incrementally do this and leave all the rest of the code as serial. Okay, it doesn't speed things up, but at least you can see that the right numbers are coming out. You can get bug-free code, but even if you do that all the way through the code, you're unlikely to get good performance. Okay, and by tearing down parallel regions, you can add extra issues in there. Really, you want to be able to grab a bigger piece of a parallel region and do something. So a more coarse-grained approach. In this example, the do loops are still parallelized at that level, but now we've moved the parallel region to be the whole thing. And where we want to do something serially, we simply put in this case, master. It could be single. Okay, quite a bit more effort and fine-grained. You have to look at a larger piece of code, but you can often do this bit by bit. I'll do the fine-grained and then move up to the more coarse-grained. And it will typically give better performance. There are other options. You've seen collapse to help things with do and for to get better load balance. I believe that was one of the examples yesterday. There's the Fortran work sharing construct, there are sections, and there's nested loop parallelism, plus the new tasking directives. So one of the things that you might want to consider, and certainly some of the best performance comes out of, is when we talk about the coarse grained, is really go right back to as far in your high up in your program as you can. It may be if you've got one routine and lots of other ones. If you can find some way of parallelizing at that level, that's the way to really get good performance. The collapse clause, you met this yesterday, yes? Is that correct? Yeah. Okay. So this is just to say, just to repeat exactly what happens for the collapse directive, and just to say that you can get better load balance with a different number of by saying collapse the loops. In this case, we're collapsing all 3 loops. Could be you only want to collapse 2 loops. By collapsing the loops, though, you do tend to lose some data locality, which is what we're going to look at next, unless you collapse all the loops. The task model. I don't know, was there a task example yesterday? Yep, okay. So very few people are currently using the task model, but they're finding, those who are finding some very good use. One of the examples I said earlier, the people who did some work 10 years ago on the GTK code, this is a plasma physics code, have recently gone in, revisited their application, and are using the tasking directives to say, I'll have one task go away and do the MPI communications, and the rest I will then use the tasking constructs around individual parts of do loops to distribute my work. And they've got some nice scaling improvements by doing that. It's more powerful than sections in that you can have multiple tasks. But there are issues to do with the tasks working in undefined order. Your tasks will be mapped onto threads, so the maximum number of threads you have has an impact on this. It's got good potential for overlapping something like communication or I/O, but again you may have problems with data locality issues. And that's because we're actually looking, as I mentioned earlier, at the majority of what you will see around these days is multi-socket, multi-core nodes. And you just saw a diagram of a Cray XE6 node, which is one example of this. So here's an example, 24 cores, that's what we've got on the Palu machine, of how this works and how you would normally think of things. So a multi-socket node, you've got multi-core processors and what you consider to be a global memory, because all the processors or all the threads that you're running on that node can see all of the memory. Okay, from an application point of view, it's a single view. And in order to allocate some memory, do a malloc, to do an allocate, you just go along to the operating system and say, give me some memory. And you don't care where it comes from because you see it as being uniform. And if you're on one single socket, like we mentioned before, there are some of these machines that will be around now and will continue to be around. So the Blue Gene Q machine will come along and it will be a single socket. That Fujitsu machine that will be built in Japan will be a single socket. But most of them will be multi-socket. Or also, if you have a GPU-based node with a single socket as the host, that's another example if you're just using that CPU where you don't need to worry. So, but in most cases you don't have that, and in particular, even if you have a single socket Manu core, it's a little bit different. Because what we actually have here is something called non-uniform memory access, NUMA. How many of you have heard of NUMA before? Okay, a fair few. Right, going to go over it anyway for those who haven't. So on a 2-socket node, we actually don't have uniform memory access. Yes, sure, you can see all that memory. You can allocate wherever you want on that memory. But there's a difference between something being local and something being remote. So in this example, and this is an image of what a node on the XT would look like on the ROSA system. 2 separate Istanbul processors, 6 cores each. Each one is attached to a memory. Okay, there's not the central pool of memory. The individual socket has a piece of memory attached to it. The 2 sockets have an inter-socket communication, This is hypertransport in this particular case. So you can see from over here on one of the cores on one socket across the bridge and up into the memory of the other socket. But you don't get that fast local memory access. You have to go through that inter-socket communication. What this means is that if you allocate some memory, if everybody allocates it on the same place, everyone's going to compete for the same memory. If you allocate it on the other node, it's going to be more distant from you. It's going to take longer to get there. So here is that specific example where I can actually now put in some numbers. Memory bandwidth on this node on one socket to its local memory is 12.8 gigabytes per second. Okay, so we talk about the memory bandwidth on the node being 25.6 gigabytes per second. That's the marketing number. And if you run a stream benchmark, you can actually get a good proportion of that. But that's because we are allocated in a way that the memory for each thread or process actually looks at its local memory. But look, the inter-socket bandwidth is reduced. It's down to 8 gigabytes per second. So whereas a core on the first Octeron could get, in theory, 12.8 gigabytes per second to its main memory, it will never see more than 8 gigabytes per second to the remote memory. Now the latency to local memory is also lower than to remote memory. But we're more interested generally in bandwidth issues than in latency issues. Now for a Cray XE6 node, the diagram Roberto put up earlier, actually this becomes 4 NUMA entities per node. Yes, we have 2 sockets, 2 of these Manu cores, but each one of those, what AMD have effectively done is take 2 of these Istanbuls and effectively glue them together onto one socket. Okay, 2 dies. You get lower clock speeds and so on because there's a lot more circuitry and so on there. And they've tried to put some nice more hypertransport in, really beef up the communication on the socket as well as being able to go off. But effectively now it's not only 2 nodes we have to look at, it's 4 of these NUMA entities. 2 sockets, each with 2 NUMA nodes. Now let's just have a quick look at cache and how that will affect these nodes as well. So you're all familiar with cache hierarchies or not? I'll go through it anyway. So because accessing main memory is slow, we have caches of varying levels. Caches were originally introduced not for bandwidth reasons but for latency reasons, to just make it so you could get access to data a little bit quicker that you'd already read in. But we also use it as a bandwidth mechanism for things where we only have a small footprint at any one time. And we have 2 types of locality as we refer to it. One is temporal locality. If we've used something recently, if it's in the cache, we can use it again. So recently used data will sit in that cache. And then also, when we make a load to main memory, because we have these cache-based systems, we never load one item at a time, we load in a big block. Whatever the system decides on the size of something called a cache line. And we get benefit here only if we're going to use some of the data that's on that same cache line. If we were going around and jumping in memory, we consume a lot of our memory bandwidth loading in these cache lines into our cache for data that we never use. And that's why caches, which are managed by the hardware, now having a lot of criticism about their utilization, and why a lot of people are talking about really having software management of these more local memory accesses being much more important in the future. And the cell processor, for anybody who ever had a go on one of those, was something where for the little SPEs, as they were called, for the little mini processors, you did all that explicitly. You sent the data there, you moved it out. It was like a cache, but it was no hardware management. But on these processors, we do have hardware management. And the idea here is that often an algorithm will step through adjacent locations in memory. So loading in all in at once is a good idea. Plus, once you've loaded in, if you load in the whole cache line, you don't have to worry about going back to main memory and the latency that will introduce. And we typically now, most of these machines tend to end up with 3 levels of cache, but it could be 2. One other aspect is that your level 1 cache will normally be for one core. Your level 2 cache may be for one core, or it may be shared between two. But your level 3 cache is normally then getting shared between several of these cores. Cache coherence is then an issue beyond the socket or beyond the NUMA entity. So those caches are storing local copies of something that's actually out in main memory. And so if you can work on something in your cache, you never go back out to main memory, you don't disturb it until you absolutely have to. But what happens if somebody else also wants to look at that memory, a process on the other socket? You've loaded in a copy and you've done some changes. It's now got to actually be able to see those same changes, otherwise we have a problem. For separate MPI processes, if all you've got is MPI, this is not a problem, because each MPI process allocates its own memory, does things on its own data, and no other MPI process wants to know about what you're doing locally. The only time that you have any data interaction is when you explicitly do the data transfers. So for separate MPI processors with distinct memories on multiple cores, not a problem. For OpenMP codes, when you have multiple threads, this can be a problem. If they're all on the same die, all on the same socket, all seeing the same data in cache, they normally don't have a problem. But if you've got somebody on another node and you've been making some changes, it's got to now be made aware of those changes. So what happens is, before accessing memory, if it wants to load in some data, a processor will check its own cache. Do I already have this data? And then it will have to have a look and say, do any of the other sockets have this in their cache? Because I don't want to get the wrong data here. To make sure there's coherency. So the caches have to be coherent, have to be up to date, they can't have any problems. Now, there are ways we can still have issues if we have this coherency mechanism in place, because once something's loaded into a processor register, you can modify it, and you're not modifying the cache immediately, so the other processor won't know that you're already doing something. We'll look at that later. This is called a race condition. So cache coherence amongst multiple cores, how does this actually work? With two single socket example here. Okay, two processors, just one level of cache. We don't want to get involved in the first, second, third level, etc. And both processors have taken a copy of some data into their cache from main memory. They've read it in. One of them wants to write something to that piece of data, that cache line, and the local copy is affected. But we're not changing the main memory at this point, because we're trying to use the fact that we've got a cache to improve our bandwidth, improve our latency. Okay, so we want to avoid that slow memory access. Right, now, on a cache coherent system, we want to write to the main memory. We have to let the other socket know that there's a problem, that we're actually writing to that main memory. Otherwise, it's got a bad copy of the data. And we'll just both start writing random rubbish, basically, to main memory when we actually get round to it. So the other processor's cache needs to be told that its data is bad, okay, or dirty, as it's normally called. It needs to therefore get a fresh copy. So what then happens is the data will go along, the other socket will go along and it will try and grab hold of your copy of the data. Once you've made once you've passed on this information, you are now allowed to write to your cache. Before that you can't, because you don't know whether the other one's going to try and do it at the same time. So you have to get this notification mechanism. Now you can write to your cache. And now if CPU 2, if the other one wants to go along and read or write to the data, it needs to get a fresh copy. So it needs to get, either you have to flush back to main memory and it grabs it from there, or some other mechanism, but as long as the memory is up to date. So on a cache coherent NUMA node, we've got a couple of terms now, NUMA and cache coherent. We have several gigabytes of data attached. You can access the memory from anywhere. Remember, local memory and remote memory, so the NUMA aspect remote memory is more difficult to get hold of from a latency and a bandwidth perspective. And a cache coherent NUMA node also has that aspect that it will keep track of the cache as well. And just to add in a few extra terms, just to finish it, yes?
But is it common to have NUMA non-cache coherent? I mean, it's possible.
NUMA non-cache coherent. Don't know of any nodes at the moment. So there have been some non-cache coherent processors around. A Blue Gene L processor, for example, was not cache coherent, but it was only one processor. It was one dual core processor, and that's why it wasn't suitable for OpenMP or anything like that. Even if the operating system could have done it, but no. Generally, you get cache coherent nodes. Still, just want to express how this works because it also is very important when we talk about race conditions. Okay. But some of the other terminology that is common place is a superscalar processor is one where it will do more than one instruction per clock cycle. And typically now things may issue 2 or 3 things at the same time, may be able to do a load, at the same time it's doing a floating point instruction, etc. An Itanium can do 6 instructions at once, but it's up to the compiler to really package those efficiently. Most modern server processors out of order. So in other words, if something stalls, if it sees it's got a problem with a load, but the next few instructions don't rely on that, it will start to continue to move forward, and then it will, when the load comes in, it will do what it needs to do at that particular point in time. This adds a lot of complexity to a chip, to be able to actually do that, to allow you to not stall and get on with some useful work. And that's why you now see a lot of the more simple processors saying, we're not going to do that. So things like an Intel Atom processor for use on a netbook, one of the things they backed out of is to make it more in order. It will stall much more frequently. And it's also for some of the very small cores that people are trying to package together to turn into accelerators, exactly the same sort of issues. Then another aspect of parallelism on the chip that we have, as well as we've got the superscaler, it's doing more than one thing at the same time, is pipelining. So typically for do a floating point multiply, it might take 6 clock cycles. It's got quite a bit of work to do. But what pipelining does, it's like a factory production line or having a set of people lined up to when you want to wash the dishes. One person will clean the plate, pass the dish on to the next person who washes it, passes it to the next person who dries it, passes it to the next one who puts it in the cupboard. Well, you don't have one person doing all those things, you have 4 people, and you can have, at each clock cycle, you can load a new plate and keep them passed along. So rather than it taking 4 people in that case, 4 cycles to go through, you're getting a plate out at the end each time. That's what modern processors are doing with pipelining, and they've been doing that for many, many, many years now. And then we have the SIMD units on these processors, double hummers on the Blue Gene P systems, and these are vector units for enhanced floating point performance. Very important these days, and getting more and more important. If you are not able to get vectorized code and use that SIMD unit effectively, you'll get poor performance. We're getting to the stage where these things are 2 and 4 issue instructions at once. If you don't use those, you only get 1 at a time, much lower performance.
And those SIMD units are part of the CPU, or
they're part of the CPU. Yeah.
The CPU, so
Yeah. And yeah, so you don't need to do anything special. It's not like going to the GPU where you've got a device and you have to deal with it. The SIMD, the compiler will just say, oh, I'm issuing an instruction. It will work out that it needs to load into separate registers the data, and it will say then with the data that's now in separate registers to actually issue the SIMD instruction. It deals with it all for you. The only thing you've got to do is check your compiler output to see if it did it. Okay. So all the compilers that we work with tell you something about what they did. The Cray compiler is a nice example. If you get it to give you a listing, it will, which gives you a .lst file, and I always do this by default, you go in, it gives you a list of your code, and then down the side it gives you some instructions about what it did. And if you see it's got, I think it's a big capital V for vectorization, if I remember correctly. Great, it vectorized that loop. And there's an example in some slides tomorrow that I'll be presenting from SADAF where we just show a little bit of an output of the compiler, of what the compiler did. So if you use other compilers, for example with the PGI compiler, another example, it will tell you what it did. The separate flag will tell you what it didn't do. Okay, it's important to have them both for it to tell you I wasn't able to vectorize that loop for whatever reason, or even I decided not to vectorize that loop for a particular reason, like it felt that you're unlikely to get a benefit from it. You can then tell it to be more aggressive, but you must be able to use the SIMD units if you want good performance, good floating point performance on these machines.
Does it work nice with OpenMP? Let's say that we have a loop that we parallelize. Is it able to say I'm keeping, let's say, a part of the array, and then I'll just pass it to the assigned unit for each course?
Yeah, it should be. It's core independent. So the OpenMP, because it's a threading model, it doesn't really relate to the hardware as much as to the software that how you're distributing the work. So as long as there's no, it doesn't find a problem where you're splitting every pair of pieces of data down the middle onto separate threads, it should be able to vectorize that quite happily as well. But again, look at the output from what the compiler says it's done. Okay, but this should all be hidden from you. It's just important to check that it's done it. Yeah.
Another question. So, superscalar processors are those that allow for simultaneous multithreading. So, what you were mentioning, hardware threads.
So, a superscalar processor in this case is not to do with threading. This is just saying any one individual stream of instructions that one thread, process, whatever it happens to be, one task is following, it will issue more than one of those instructions at a time where it can. Like it will say, I'm going to issue a floating point instruction to do a multiply add, and I've got to do a load at the same time, so I can keep the data streaming in. That's a superscalar processor, and you might find that typically they can issue, say, 3 instructions at the same time from different types.
But the point is, should they be all from the same thread, or they can be from different?
They will all be from the same thread, because to change thread, they will all, if they're all on the same core, and if you're running one thread per core, then it's just from the same thread. If you are overloading a core with multiple threads, the type of cores we have, then it will have to do a context switch anyway, which takes a huge amount of time. So effectively it's all one thread. Okay, it's just one stream of data. But this again is taken care of behind the scenes. Here I'm just explaining some of the other features that of parallelism particularly that you get on modern processors. But this one is probably the most important, because you should really check that. So anyway, do we need to add this OpenMP to our MPI codes? For pure MPI, we don't need to worry about cache coherence, as I said. You allocate your memory, you don't share it, so that's one advantage of just using OpenMP. And because you have to think about every transfer, you think about the impact that has on your performance at every transfer. And if you do a collective operation, you think about what that's doing to your code. Okay, so it's an advantage to have to think about every single thing you do. The disadvantages are you have to think about every single thing you do. So it's a double-edged sword. It does have a good purpose, but it actually causes you a problem. You want to be able to take advantage of memory speed with transfers. What do I mean by that? I mean, if you have 2 processes and you want to pass some information around, then you have to put it into a memory location. It will get copied, and the other one will then see it in its area of memory. Now, in the simple case, it may be that one of them can copy from your memory into its local memory before doing some work. The more traditional way has been it copies into an area of memory for the operating system, which does a copy into the other memory, and then you can look at it, which causes extra copies. pure in a threading model, process and thread B wants to see whatever thread A's just worked on, it just reads the data and it doesn't have to worry about the transfers. And MPI calls can have a large overhead. That's why some of the overheads that you see in other libraries, so I didn't mention Shemem, but Roberto did as an example. This is a much more lightweight library normally than MPI when actually doing a lot of calls. So it may only had a few nanoseconds over the underlying hardware. MPI typically adds at least a microsecond by going through a more complicated software stack. So what are the advantages of threading? Why would we want to do this? Well, reduce that communications overhead on the node, and it's all just on the node, of course. We'll reduce memory usage. That's due to two different aspects. One is to do with whatever the operating system says each process must have for its own sake, as well as for replicated data. A lot of replication in your MPI processes. If you may only actually need one copy of these things. We've got a potential to overlap our computation and our communication a little bit better by threading models. And so we also may get some better load balance. That's depending on your application. Just mention the Linux operating system now, because the operating system is important, particularly from the point of view of memory allocation. And the big thing I want to talk about now for a while is affinity. So CPU affinity is when you pin a process to a particular core, a process or a thread, some task. If you've pinned it there, specifically, if the operating system comes in and says, and the operating system is the ruler of the empire on any of our nodes, okay? If it needs to do something, it doesn't matter what you're doing, it's just going to kick you out and do what it needs to do. Well, we've now got 12 or 24 cores on these nodes that we're looking at. It could fit anywhere. So it may come in onto your application process. What this basically says, if you've pinned the processes or the thread, okay, when the operating system comes in, I'll get out of the way, just don't go and tell me to run somewhere else instead. That's if you don't have affinity, if the operating system or something else comes in, it could be also an MPI daemon or something on one of these nodes. The operating system may say, well, it'd be a bit unfair to leave you sitting around waiting for the core. I'll move you somewhere else, and then I'll move somebody else out of the way, and you start to swirl around the threads. CPU affinity, it doesn't do that. It just says, okay, you've told me that you're prepared to wait, so you're going to have to wait. Now, when we're looking at HPC scenarios or HPC systems, we only typically want to run one application on a node at a time. Okay, we're not talking about the sort of things which is still with high throughput computing, for example, where you might have lots of people coming into the nodes at the same time, and certainly not things like web servers or whatever a bank may do with really a lot of different things going on, or your desktop. HPC, single application running on a node. You're therefore not so likely to get an interruption from those tasks. Also, if you take an example of the Cray, as Roberto said, one of the things they've done is to make the Penguin thin, is to get rid of all the stuff that Linux might otherwise do, so therefore there's much less on terms of daemons or interruptions anyway. So that's CPU affinity. Memory affinity then is the allocation of memory close to where you are. Okay, as close as possible to that core on which your task, your process or your thread, which makes that request, is running. Now actually, it's not when you do the malloc or the allocate statement that's important here, it's when you actually physically touch the memory. At the time you do a malloc or an allocate statement, it's actually very quick. The operating system just looks to a table and says, yep, I haven't allocated all my memory now, here, have some. Or actually, in most cases on Linux, it doesn't actually care about whether it's allocated all its memory, it may give you it anyway. This is a different issue about out-of-memory errors on these machines. The standard Linux behavior is to allow you to over-allocate the memory. Not something we're particularly interested in HPC. But when you have a disk drive that you can swap out to, etc., it becomes more significant. So it's when you actually touch the memory, that is the first time you go along and say, set it to 0, or whatever else you do with it, that's when the memory is actually allocated from a pool on a piece of memory, and that's where you want memory affinity to be close to you. And this is referred to, therefore, as a first touch policy. It's not the memory allocation. Is that clear? Yeah? Okay. It's significant because, therefore, if you really do want things to have that memory affinity local to you, it's normally very useful to allocate something. You may allocate it, for example, from one thread in a multi-threaded program. And then, if you're constantly going down looking at the same data from do loops, the first thing you should really do, or you may want to consider doing, is create a do loop just to set the data to 0 with the same thread pattern that you would have through the rest of the code. It will cost you a few microseconds, milliseconds, or a second, but on a 24-hour run, that's not that important compared to the performance loss you would otherwise get. Both CPU and memory affinity are important if we want to maximize our bandwidth. It's no good having memory affinity with no CPU affinity, because all you'll do is you'll allocate memory locally and then you'll move somewhere else and it's no longer local. Okay? So both of them at the same time. And if you don't get memory affinity correct, then your bandwidth will be reduced as you go off socket onto that remote memory. So by default, a NUMA-aware Linux kernel will try to use a first touch policy when allocating memory, but you may want to enforce it. There are tools and libraries available to enforce CPU affinity. So Cray's app run, or if you're on a different system, it may be Slurm's srun or something else. They can enable CPU affinity by default, or they can allow you flags to actually say that you want that CPU affinity. On Cray system, for example, apprun -cc CPU, I think, is the correct thing to say. Give me a separate CPU with affinity for each of my tasks. OpenMP has support for CPU affinity, and many compilers also have CPU affinity settings. So I want to say why is this memory affinity important for bandwidth change. So we're going to use the stream benchmark, just an example, on a Cray node to show you what happens using 3 different types of memory allocation policy. Okay, so the first is the default one. So the CPU and memory, each OpenMP thread uses first touch on its own memory. Okay, so I start up OpenMP threads, touch the memory, and they will get it locally. Second, we're going to do a crisscross pattern. Okay, so this is to say a thread on the different socket touches the data. So what I'll do is actually I will get one set of threads to allocate some memory in a way of then swapping around the threads so that it works on a different part of an array. Okay, particularly, for example, if I say I want an array with in Fortran leading final dimension 12, or in C the first dimension 12 on a 12-core socket, I allocate memory if I'm thread 0 for thread 6 for the 6th dimension. Then when I come round to the stream, I use 0. So I've been allocated in the wrong way. The third method is where all the memory is first touched by the master thread, so I do it just with one thread, and therefore all the memory will be allocated on my local node, and then I start up the OpenMP threads to run everywhere. So they're all now concentrating onto one node. Okay? Do you understand what I'm saying there? Yeah? So we're trying to make sure as well the data set is sufficiently small that it can fit in the local memory of one of the sockets on the node. The reason I mention this is because many people who implement OpenMP don't do the first touch, and then they start to use OpenMP directives, and typically we don't want to set memory to 0 or do anything with memory that we don't need to, because it takes some time. And if you're in a loop, sure, you don't want to be every way through the loop setting something to 0. In the past, that was an optimization. One of the easy optimization techniques is to go in, see somebody setting the memory to 0 when they don't need to, because it's then set afterwards, get rid of that. Well, with OpenMP threading, it can actually be important to do it but you want to do it as far out as possible so you're not consuming unnecessary cycles. So be sure to put OpenMP directives around your first touch routines, otherwise you might complain. So let's have a look at how this works. Well, got a few examples. So we'll begin with an Intel Nehalem machine before we're looking at the Cray ones. And this is a machine called Julia. I had a little bit of a problem with actually getting Linux to actually allow me to pin myself on these things, so I just ran the thing many, many times until it had settled down. So the memory affinity produces the best numbers. The inverse affinity, where they're crossing over onto the other node, produced worse numbers. The first touch all onto one socket produced the worst numbers, okay, in all cases. But that's a third drop in bandwidth, okay? And the inverse affinity is just to show you an alternative, crazy way of doing things. This is what you want. This is what you typically will find a lot of people do because they don't set that memory to 0. Okay, and that's gigabytes per second. Aggregate gigabytes per second across all threads. Right. This is now the XT5 Rosa, one node of Rosa. So we've got 2 sockets, 6 cores. Right. And I use AP run to enforce CPU affinity. Okay. What we actually see here then is we get a variety of different memory bandwidths depending on the stream benchmark we're running. The inverse affinity, where everyone's trying to compete for that 8 gigabytes per second hypertransport, causes a dramatic slowdown. This, remember, was 25.6 gigabytes per second in theory that we could get at the top. I've perhaps not put on all the best compiler options here. The inverse affinity drops to about half, and the first touch, okay, in one case it's better than the inverse affinity, but you can see that the standard is half, in almost all these cases, is half of what the memory affinity you want to get is. Sorry, what the memory bandwidth you want to get is for your application. So it's very important to consider. So that's on Rosa, the XT. Now we look at an AMD Manu core. This is Palu. This is the machine you've actually been running on. And now we get even more dramatic. The black's perhaps not so easy to see on the purple, but the columns are the same order we had before. And now we have effectively 4 sockets of 6 cores. It's 4 dies because the Manu core has these 2 dies put on. Okay. And what we get is standard memory affinity. We're getting close to what is the peak theoretical performance of a Manu core, which is reduced on what we will see in the Istanbul, even though the memory is the same for various reasons that I won't go into. But memory affinity here gives good bandwidth. Inverse affinity is about half of that. But now the first touch policy is much worse. We're all now competing for one little block of memory. In fact, it's not even a 4-to-1. Remember, we've got effectively 4 nodes, each with their own local memory. They all should be competing for all 4 of those sockets for one memory. It's not even 4-to-1, it's worse than that. So if you don't do an allocation to get memory affinity on Palu, you'll be in real trouble if you're memory bandwidth bound. Okay? Understood? Yeah?
Just a question. The first touch policy is on a memory page basis, so you can have different parts of the same array actually being closer to different cores, right?
Oh yes, yes. It's like I say, the malloc or the allocate, yeah, is saying give me some memory or give me the right to access some memory. You're right, it's on a page by page basis. So as Roberto said before, each page is 4 kilobytes. So as you go through, if you really wanted to, you could say allocate the first part of an array, allocate the next element 4K later. You don't physically need to load the cache lines into memory. You just need to get it so that there's one element, 1 byte out of every 4K that's being touched. You're right. Should have made that clear. Thanks. So it's done on quite a reasonable size block. If you go onto large pages, you can then get up to megabytes worth at a time. So it's important to make sure you get that memory, that first touch policy correct. Okay? So as I said here, only one of those mini sockets is available, and that really gives you a bad bandwidth. Okay, that's one of the more important messages to get across about performance of OpenMP. Also want to talk about Open Operating System, how it separates the processors. Okay, this is processes, not processors. Each one of of your processes gets a separate address space for a variety of different things. It will have its stack, its heap, its text, data segments, and so on. I don't know whether you're familiar with those different breakdowns. Basically, it's got its own memory split into its own little sections. The stack becomes significant when you have, because it's normally a small allocation, and if you have a lot of temporary variables created in subroutines, you can actually sometimes get a segmentation violation because you've run out of space here. Process 2 has its own copy of the same thing. Now, one process cannot see the memory of another process, and that's why we don't need to worry about cache coherency for the MPI space, because each one of these is a separate process. But we do need to therefore use kernel level routines to enable message passing. And this means it's unnecessary waste of bandwidth if we're on the same node, because we have to ask the kernel to do something with the data we've got, move it somewhere else before the other process can see it. Multiple threads share the same address space, so they don't have to worry about copying any memory. They can just go along and look at what they want to do. So the communication mechanisms for message passing are that the message may need to be buffered, placed into an intermediate step before being moved on. There might be multiple memory copies. So if you want to copy 1 gigabyte of data from one process to the next, it might actually jump around several times in a normal MPI implementation, and you might find that you're getting a quarter or less of your memory bandwidth because you're doing multiple copies. But effectively, all this is just a copy between two processes. And so there are some libraries that have been developed to minimize these transfers. So on the Cray, you will see XPMem. This was developed by SGI, although Cray may actually say it was developed before that by them, before giving a branding or whatever. And there's also something now called KNEM that's being exploited by OpenMPI. And what this is an extra layer which allows you to actually almost bypass the kernel by saying, I want these things to be able to share where they can see, so I can drag the copy across in one go. You still have to do a copy, but it reduces the extra copies that the buffering would normally do. But OpenMP threads get around that altogether anyway. They can I just read your data. I don't need to copy it somewhere before reading it. So, a copy example. We're not actually even doing a copy in the OpenMP thread case. And look at the speed. We have two kernels doing effectively the same thing. Here we have to do an MPI send receive, and here we're just saying I just copy from send array to receive array. Okay, in each case. The OpenMP implementation on both Cray systems is 2 to 4 times faster because we don't have to do any of the intermediate copies. So as I said before, the memory of an individual process has multiple different steps, and each of those consume valuable memory. So if you're a memory-bound person, if that's why you particularly want to use OpenMP, getting rid of these extra processes can be quite significant, as well as having all the extra data even in your code that can be significant. And for example, MPI may actually also, when it fires up, say, well, well, I'm going to pre-allocate certain amounts of storage space that I need later on for MPIIO, which you may not use, etc., etc. And if you do have a hard limit on the amount of memory you can allocate, depending on whether the kernel is saying you can over-allocate memory or not, as I said before, this could be quite significant for you. And also there are some non-scale, even in almost all implementations have some problems with scalability in the MPI implementation, that the increasing number of ranks does cause a growth in the amount of memory that's required. And most implementations put these as high priorities in trying to reduce that, but it's still there. And there are other libraries that may also require extra memory. So if you can get rid of all these things, then you can bring down the amount of memory you require. For threads, you don't need to worry about that. If you, in MPI or anything, if you take a fork, which is effectively what you're doing, a Unix fork, when you create a new process, that's what copies all this memory, the separated address space and so on. A thread's very lightweight. It just sees what you saw before, and only afterwards does it create new variables. Only one copy of the MPI buffers and all the rest exist because it's only one process. And so you can reduce that overhead from multiple processes. It may or may not be important. On something like our current systems, it's not that significant. But over time, we expect that we won't be able to buy more and more memory to keep up with 2 gigabytes, 1 gigabyte or so on per core. Okay, and some people are predicting that the memory growth rate that you can put in these machines will drop quite dramatically. So far, we've been able to keep a reasonable amount of memory per core. That may drop, and then that's when this will become significant. Particularly from the point of view of the memory itself per core will probably drop, and the number of MPI processors you need will increase, so that buffering I talked about will then increase with it for those non-scalable parts of the library. But then we may also be able to benefit much more significantly from the reduced memory requirements of the application itself when using MPI OpenMP. So here's an example, a crude diagrammatic example of how halo regions and replicated data work in MPI. So for people who are, most people in most codes in scientific computing have some sort of halo region, ghost region, where they're going to transfer data around. They have effectively a local copy of some remote processor's memory. And these things need to be copied frequently. They consume a lot of bandwidth as well, for the reasons we mentioned before, having to take multiple copies with MPI. But using OpenMP, we can reduce the size of these halos where we can get everybody to see the same space. And there are other data structures as well as these halo regions that, for example, may benefit. And it also, as I said, it reduces communication requirements, it reduces bandwidth. So those MPI processes, for example, if we had 8 processes, goes to 8 threads on one node, diagrammatically it will look like this. I had reasonably chunky, big halo regions. What we've actually saved there from the storage, this is just me individually dragging over the little bars on the PowerPoint to give you an example of what the actual size would be like. And yes, I've spread them out slightly. But you can see that's a significant amount of data of our overall problem, if that was actually real allocations in your memory. This is again how using threading on a node for for memory bound problems could give you a big benefit. Okay? And say it's not only saved storage, it's also some saved bandwidth in there.
So you've lost a bit of memory affinity by doing that, because you could have allocated each chunk with its halo on the individual thread, and then you would have ensured that it's local to the thread.
Okay, I could have allocated, you're right, I could have allocated the halo, but then I've still got to copy it. So at some point I'm still have no affinity during the copy.
Yeah.
If I need that halo region many times, and I wanted to get it, you're right, then it may be better to take a local copy. But but it also then depends, but that's if you're talking about memory affinity. You're right, good points, I like these. But there's another example. If that instead was a dual socket machine, each with 8 cores, like an Nehalem EX, for example, and you decided that actually those MPI processors you're just going to do on one socket, then the memory affinity problem is better. So yeah, it's a good point. You have to always think about memory affinity, which I haven't forgotten in 10 minutes, but it was worth mentioning. But weigh that off against communication and against storage. And certainly, I should say that the majority of people we have running here, MPI OpenMP hybrid, very few times do we see people who are actually running more than one node of OpenMP anyway. I should have said that as well earlier. People haven't got their head around how to actually do the parallelism beyond that. So Amdahl's law for strong scaling is a limiting factor for the parts that cannot be parallelized. And we've got away with this because, as John Gustafsson said, well, we do weak scaling all the time. Well, we can't really get away with that. And it also looks at whether you've actually, in the simplest case, most people consider it, you've either fully parallelized a region or it's fully serial, and that's not really true. You get a mixture of the two in there. So typically computation, the part where you're trying to get that linear scaling, might already be efficiently parallelized. Okay? And if it's been efficiently parallelized, the computational aspect itself, then you don't gain anything from OpenMP. You can get memory bandwidth limitations in that actually mean that Amdahl's law is a little different because you're not talking just about what compute you can do, but about what memory you can access. And that can therefore slow down the parallelizability of a region. Even if you fully parallelized it as far as you're concerned, it might not be running as fast as something else. Communication is similar. You have some parallel processing overheads anyway, and then you have I/O and other serial parts of the code. Now, let's go back to a domain decomposition example. In this case, it's on a 2D grid, which would be applicable to something 3D grid like the Cosmo climate code, where you're actually not parallelizing in a third dimension. And here we've got an idealized 2D layout. For P processors, we have each with m by n grid points. So an individual processor m by n grid points, 2m plus 2n halo points here. If we then say we'll spread that onto 4 times as many processors, each processor therefore is getting a quarter of the region. But the number of halo points has only gone down by half. Okay, so we've lost something there in terms of the amount of storage and the amount of bandwidth that we're going to have to do to read those things in. Serial parts of the code don't change. And we assume that for the I/O, the same amount of data for the whole problem is going to be output at each time step as well. So using 4 OpenMP threads rather than 4 MPI processors will keep that halo region constant. We wouldn't increase the size of the halo region, the memory accesses, and so on. And so scalability, ideal scalability for a 2D grid-based problem on P processors with P processors, computation is typically the bit that you can get scaling quite nicely if you don't have low balance problems, etc. So you get some minor scaling problems to do with halo memory bandwidth and so on, vector lengths, software pipelining. The communication, if you start to distribute amongst different processors, scales though more like order root P. So it's a major scaling problem when you actually get to the halo part, whether it be because of memory bandwidth or communication. And that's why we don't necessarily see the perfect scaling that we would otherwise see. And then the worst bit is the I/O and serial parts where there's no scaling. And I/O is typically quite serial. Once you've got above a certain number of processes, once you've saturated your I/O bandwidth for a particular problem. And so then to put this in some numbers, if you had, for a theoretical example here, an 8 by 8 cube with one element, a halo is a 10 by 10 by 10 cube. and that's half of the grid points are halo regions. And even growing that something, you can still stay with 30 or 17% halos. And you've got to think about how that fits into some of your particular applications. And then we'll take the example of the Cosmo 2 weather prediction model. So an individual process is typically a 20 by 10 distribution of grid points with 60 atmospheric levels, but we're only interested in the 20 by 10. And with a halo width of 3 elements, that's a grid to halo ratio of 50% of the zone is halo regions. So that causes problems for how much work you can do, how much memory bandwidth you have to do, etc. And it's not, replication is not just a structured grid problem. Typically, you will have a lot of replicated data in any of your problems, unless you're something where you're down to a map-reduced Monte Carlo type problem where it's you go along and deal with something, come back to me with only 1 or 2 little numbers at the end. Another thing to mention is the stop-start mechanism of MPI. And this is something that's just the way we code things. We do some compute, then we communicate, then we compute and communicate. We tend to do this much more than we need to. You can use asynchronous methods, but the collectives at the moment are definitely non-blocking. And so that means we'd really like to have those asynchronous collectives in all our implementations, and they are part of the standard now, an MPI I-all reduce, an MPI I-all to all, but fortunately we don't have them just yet. So we have to block. If a large part of the application does that, then this will cause a bottleneck at runtime. Asynchronous implementations, this was something we mentioned earlier about the threading. So to a programmer, you typically look at the asynchronous and say, oh, actually I'm going to use iSends and iReceives because they're going to help me. I just hand it over to the MPI implementation, you get on with it while I do some other work, and I've overlapped effectively with my computation and my communication. But the internals of most implementations don't do this. So they're not threaded. So the communication will only take place, and an MPI call takes place when it has access to whatever it did before. And that typically for applications means either when you issue the asynchronous call or when you issue the wait for that call to complete. Now there's a reason why you might want to do this on a Cray system to do with pre-posting receives, which I don't know whether you still need with Gemini, do you as much? Probably not. But it was a C-star, was one of the big messages that people like Roberto would say is pre-post your receives, because that actually then gave information to the communication chip itself to be ready for this. But typically you don't get any help out of this. OpenMPI has introduced its threading support in its internals, but I haven't gone through the code because it's millions of lines to find out where they have and where they haven't been doing this. So typically if you're going to get something out of an asynchronous call, you rely on the hardware being able to do these transfers for you, and the MPI implementation then being able to effectively offload. And certainly Gemini could do this for you. Roberto would be the person to tell you how effective the MPI implementation does that on top. Or he will find somebody who could tell you. And as I said, if it doesn't take place then, it will probably take place when the wait occurs. And so then, just to finish off with the dangers of OpenMP and some things to consider. So it's not as simple as it first appears, or actually it is as simple as it first appears, but not if you want performance. So you can develop the code incrementally, but you have to do the whole code if you want to get some speed up. And it's not just about adding a few directives. So you don't need to think like you do with MPI about every single message that you're passing, how costly is this, do I really want to do it, do I need to reorder things, parts of my code more efficiently to be able to do those communications. You just typically go in and you can add some directives. But you do have to think as carefully as you would about any MPI implementation, if you want to get your code working well, get it working fast. So we'll look at some of those things just in a moment. Just for a second, I want to come back to what we talked about earlier with cache coherency and mention about race conditions, because this is another danger that you will see. So cache coherency, if something's sitting in the cache, but you want to write to it, and somebody else has got something in their cache, then there will be a mechanism so it will know that that's bad data. But once you load something into the register on your processor, you do things locally. You don't do anything back to cache until you come to store. So therefore, the other processor, the other cache, any of those mechanisms doesn't know what you're doing. So this time, it's dangerous. Okay. Oh, it's gone off. So in this particular case here, we'll have value 2 in the middle is a piece of data in memory or in cache, and both threads read a copy of this variable. So at the moment, the value of this variable is 2. Now, one thread reads in that data and adds 2 to its copy. They've both got a copy of this data from memory. They've added 2. This takes place in the registers, so it's not taking place in the memory. It's now private. It's gone into a separate little room to do its calculations. Okay, the second thread has got into another little room and it's added 3 to its 2 to get 5. Now, if both of these things were in a serial code, those instructions, you would follow one instruction to say add 2 to my copy, and then you would follow the next instruction to say add 3 to my copy, and what you have on the right hand side would be 7. But neither of them has 7, and now they start writing their data back. They've come out of the room, they've done what they wanted to do, and they now put it back into the cache or the memory. And we'll say for this purposes it's memory. So the first thread will write back the new data, and it will put 4 into memory. Memory's been updated. But the second one comes out of its room, oblivious to what the other thread's been doing, said, well, I've updated I've done the calculation you asked me to do, and he puts 5 into the memory. And so we end up with a memory location that has a result of 5, but there were 2 calculations going on. We should have got 7. Okay? This is what we call a race condition. Both the updates have not been accounted for. Both of them are racing to do their calculations and racing for the data. This is one example. The sort of, you could have got 5, you could have got 4, or you could have got 7. It's unpredictable. It's dangerous for that reason. This is something that you really have to be very aware of, and that's why you have to be aware of where you have to use atomic updates, critical sections, some of the things that are not just as simple as putting a do loop in. Okay, and that's why we have extra constructs for even more, where this becomes more common, reduction variables. Okay, so if you have a reduction plus or whatever and a separate variable, they will all take their own copies, work on their own copies, and then they will add the copies together at the end. But this is one of the most dangerous things that you have to be aware of. Did you understand that example? So as I said, atomic and critical directives are the things to look at whenever there's the risk of a race condition. Another thing to be aware of, and this will not affect the results of your code, but it will affect the performance of your code, is something called cache thrashing, false sharing. There's all sorts of different phrases that people will use for this, but it's actually now something that's to do with that cache coherency protocol that was there to protect you, but actually causes you a problem. And that is because, remember, when we load in data into our cache, we don't load in what we actually want. We load in a cache line. On an AMD Opteron, we'll load in 64 bytes at a time. 8 double precision numbers, 16 single precision numbers, whatever you want to look at it. Now, if you go too fine-grained in where you're actually accessing this data, you can have this effect. Two threads want to write to different elements in an array, but those elements sit in the same cache line. So what actually we have here in this example is they've loaded in the cache line, and this is where they actually want to do the writing. Proc1 writes to the first element of the cache line, and therefore it has to send, if you remember the way that this has to work earlier, it has to send a message to Proc2 to say, you loaded in that cache line, but it's no good anymore, it's dirty. Okay, so that knows its line's invalid. This can now write its data. Proc2 will therefore now be able to go along and read in this cache line. Now, in this worst case example, Proc2 then writes its data, and as it does so, it has to say, Proc1, I'm about to write the data, your cache line's now invalid. Writes its data, and then Proc1 has to now reload the data. And then this cycle repeats. What actually is more likely to happen is this one invalidates the cache line, starts writing, and keeps invalidating the cache line, and you serialize execution. But that's the best case scenario. In the worst case scenario, you could get something which really slows things down, and you get an effective slowdown compared to your serial version, which is probably not what you're looking for. Okay. So be aware of this, be aware of where your data is stored, and try to make sure that at no time do you have multiple threads accessing, for writing, reading's not a problem, but for writing, adjacent elements on the same cache line.
Basically, in this example, if you're showing there is no danger of our data, but because cache work the way it works, operating systems think there is something wrong. So do you have, as a programmer, do you have the possibility to say no, everything is okay in this case?
So there's no danger in this. You're right. It's not a dangerous thing like a race condition, because this is all taking place in memory or in cache. So everything's always coherent. It's exactly that problem. It's always got to be coherent. If it started, because this one is wanting to write, wanting to write to an adjacent element. You're right. It could write it independently, but the actual processor architecture of all machines these days that are cache-based can't know that, and it can't take account of it. There's no way of telling it that. The only way, it would be very difficult to do anything with this. All you'd be able to do effectively might be to take a local copy, write them separately, and then get one of the processors to read in all the copies and write it back. It's not an easy thing to get around, and that's why it's just try and avoid it wherever you can. Okay. Yeah.
About the race conditions, they are very often stressed as particularly dangerous things that can happen, and that you have to use atomic statements, barriers or whatnot in order to prevent them. But doesn't it mean in the end that you serialize the code as well, and that you might better think in terms of, I never want to write to any I never want to write to any variables that are shared by several threads. Want to make sure it's either local, or you write into an array where you know by array index that is coupled to the processor ID or to the thread ID that I'm safe. And if I cannot do it like this, then I have to think about the algorithm.
Yes, and that final bit is the most important. On anything you do with these things, think about your algorithm before you start. But it depends. If you have something which is very little work in a parallel region, yeah, on each iteration, and there's an atomic statement in there, you're absolutely right. And this is really slowing things down, because there's a chance the synchronization of the whole thing will make it much slower. If you've got a for loop in C or a do loop in Fortran, for those of us who are Fortran programmers, and there's quite a bit of work to do, and then there's an atomic or critical, and then there's a lot of work to do, or even if there's just once through the loop, quite a bit of work to do, you might not see it, you might not notice it that much. So it's very much an idea of, yes, of how much work is there to do in there. If you can find an alternative anyway, then great, but sometimes you can't, particularly if you've got something where you may be going through some loops and somebody's updating a variable depending on a condition. And everybody else then has to check that variable. It can occur. So yes, algorithms, have to think about those. Yes?
Just for example, so suppose we have two loops, and we have static and chunk one. So would it happen? And we have two threads.
Right.
So this would happen.
So if you've done schedule static 1, 2 threads, and you're going through, yes?
So the way to avoid it, just to make a larger chunk, for example.
Right, so that's why these days, typically, although I don't think there's anything in the standard, typically when you come to a do loop, if you don't say otherwise, it's schedule static as wide as I can make it. I'm pretty sure that's the same, that's what every implementation will do. But yes, it's making sure you can avoid it that way. Similarly, be careful therefore if you want to avoid load balance, if you try doing something with dynamic 1, so you can say everybody will try and grab as soon as they've got some space available, you could get the same problem. You're right. Yeah.
Is there any smart way to diagnose that, apart from just looking at cache metrics?
Yeah, well, cache metrics would be a good one, yeah. Comparing a serial code to your parallel code and seeing the big problem. You mean a priori? Not that I know of, I don't think, no. Because it's a performance issue. There are tools available to do a lot of things in OpenMP. And so when Ralph Robinson had been coming in previous years for the MPI OpenMP course, he would always insist we got the Intel thread checker and give some examples of how it will tell you, you've got a potential race condition. You're doing things where you need to have reduction variables and so on instead. A variety of different things it would really tell you. But it couldn't tell you anything about this, I don't think, because it's a performance issue. It's only at runtime that you really see the thing. But, yeah. If you can avoid writing to shared data, that's the key thing. Sorry, shared cache lines. Okay. Then there's an issue of thread creation, overhead, and synchronization. Creating and destroying threads takes some time. But it depends. Various people have said with various compilers who have their own implementations, how long this can take, and it may or may not be significant. Now, in theory, each entry and exit of a parallel region would be a fresh thread creation and destruction area. But in reality, that isn't normally the case with most OpenMP implementations. They simply put threads to sleep. Okay? And you might be able to see this by looking on a compute node and looking at all the threads or processes alive, and actually you may see some things that are just sleeping. But in any case, for OpenMP, you enter a parallel region and you leave a parallel region, it does synchronize all the threads. It's a barrier. So that's a synchronization point you might want to want to avoid, because that creates an overhead. Therefore, having a larger parallel region and more work sharing constructs within it rather than destroying the parallel regions is much better. That gets rid of some of the overhead. Yeah.
If they were destroyed, the first touch policy would work at all, right?
It wouldn't work. Okay, it would only work if when it recreates the threads, it puts them onto the same places as it did before. But yeah. And if you therefore, for example, that's one of the other reasons why changing from, say, running 12 threads, and the next area down you might say, well, there's not much work to do here. I'm actually going to tell the parallel region to only create 4 threads. This is not a good idea anymore, because you'll probably lose some affinity. But yeah, that's why they tend to keep things alive. And the threads stay alive. As we said before, the tasking constructs, then you can create as many tasks as you want. They're thrown out to the various threads, but the threads stay the same. For some tasks, because of this, because of the overheads that are involved, it's often useful to just duplicate the work. Okay? on a local copy of a variable or whatever it happens to be. You may just want to duplicate the work, particularly if you're doing some reading or whatever. In MPI, you might do this yourself anyway. In other words, if you were just writing an MPI code rather than OpenMP code, you might come to a piece of work and say, oh, I've got to calculate something that actually would be the same on every processor. For example, you may have done got the max value for something with an MPI or reduce. Based on that, you do some local calculation that would be the same on every processor anyway. You'd probably still do it, rather than having one of them do the calculation and then have another synchronization. And for best performance, when you go through and you have do loops, for loops, consider that looking whether or not you can get away with the no wait put on the end. That avoids synchronization, allows things to continue as far as they can. Otherwise, by default, you do a for loop or a do loop, and at the end, it just waits till all the threads get there. And if there's not that much work, that's a bit of a problem, particularly if you've got quite fine-grained parallelism. So look to see if you can get away with no wait. It may be that you can't, but have a look. And then finally, then, just to say, user-level thinking. So the most difficult problem of getting performance for MPI programmers moving to OpenMP is that it appears to be easy. As I said before, reiterate several times, MPI, when you're writing an MPI code, you do have to think about everything, because you're going to type in an MPI call, and so you will actually also think about whether there's the right place to put something, whether you can move things around, whether you can compact some of those data transfers, etc. OpenMP, you tend not to think about those things. And so there are some invisible things that performance problems. Consider memory locality. Make sure you do the initialization of the data, and initialization is the first touch. And the first touch, as Oliver pointed out, only actually needs to be on the page. You don't necessarily need to go through the whole array, but whether you will use those memory locations. Now, this next one's very important as well, and that is be careful where you put your directives. If you go along and put OMP do or for with your pragma on a particular loop, you might get a problem, in that I'm sure we're all very good at knowing how to nest do loops effectively for cache utilization, but if we're not, the compiler will normally see it and do it for us. In other words, if you've got an IJK loop in the wrong order, so that you're going to go through cache in a really bad way, the compiler will come along and say, well, actually I'll reorder those, make it much more efficient for you. Okay? And you can see that typically in your output from your compiler that we talked about earlier. It will tell you it's doing these things. If you put an OpenMP directive on a do loop or a for loop, you've told it where you want the parallelism to be. It has no freedom anymore to help you out. Okay? So you must go through and check that you're not just relying on the compiler being clever and doing nice things for you. You also then have to think as well about the affinity effects that actually also brings in, whether you with the reordering. And that therefore can quite easily slow your code down significantly by having more processes, because it's just got rid of something that sped it up by 20 times in the first place. If you have a lot of MPI traffic, try and make sure you use the simplest of these things. It may be that single, and MPI thread single and funneled and serialized are the same, but try and avoid multiple if you can get away with it. Try to make those parallel regions as large as possible. It may be you can do a parallel region around almost the entirety of your your code with separate threads, and then get them just reading each other's memory to a great extent as if they were doing MPI communications. And that's how some of the best performing codes work. Use the no wait clause wherever you possibly can. This does imply that there's no flush. One other thing that you do at the end of it, whenever you have the end of a do loop or whatever, is it says make sure that everything's coherent. All the data in the registers goes back to memory, or back to at least to cache, so you avoid any race conditions. Actually getting rid of the no wait doesn't force that anymore. So you just need to be aware of that. And so those are the main performance issues, and I've overrun, haven't I, dramatically? You should have told me.
Well, with the what up on way
Yeah.
at 2 o'clock.
Okay. There's still plenty of time for lunch. Questions? Okay. Great. Enjoy your lunch.